Okay, so welcome to Math389 Advanced Applied Analysis. And so what I want to do today is I want to continue with random matrix theory, in particular doing the part that I thought we had done to explain why we were doing all these semicircle and Gaussian calculations, and now see why we're doing it. And it all comes down to trying to count how many ways are there to match things. And once you know how many ways there are to match things, then you need to calculate what is the contribution of the matching. So it's a two-step process. Before we do any of that, we have to say why what we care about is now related to counting these matchings. And this is the beautiful subject of random matrix theory. So we'll revisit the semicircle moment calculation we were doing before and talk about another way to just quickly do the calculation. We'll talk about how to set up the limiting spectral measure calculations. This is what I thought we had done, but we had not done, not a big problem. Then we'll do the odd moments vanish in the limit, which means we don't have to worry about them. So we only have to worry about the evens. And then we'll show that the even number the moments of the even powers are related to the Catalan numbers. And this is Wigner's wonderful paper, The Unreasonable Effectiveness of Mathematics, that you keep seeing the same thing in such different places. And then we'll have to calculate what their contribution is, and then we will calculate what that is, and then we'll show in some cases that if you have a crossing matching, there is no contribution in the limit. I'm not going to do the proof fully rigorously. We could. I think there's other things that we want to cover. And again, the goal is to just show you a little bit of what's out there. All right. So last time we were looking at moments of the semicircle. So the 2mth moment, we had a certain integral to do. And at some point, we had an integral like sine of 2m theta. We were integrating from 0 to pi halves. And we were playing some games like this because of just changing variables and whatnot. We got a nice recursion relation. But we had to calculate integrals of high powers of sine. And we had the great comment to write sine in terms of exponentials, expand things out. And then we had to be clever, and we had to notice that because the left-hand side was real, all of the imaginary stuff has to vanish. We don't even have to worry about it. It has to be 0. The danger in life is, what if you're not clever? Well, there's other fields like economics. So what do? You want to try to maximize the likelihood that you observe something. So instead of integrating from 0 to pi halves, if I'm integrating sine squared, what else could I integrate from? Instead of from 0 to pi halves, so if we want, so let's say 2m is greater than or equal to 2. If I want to integrate from 0 to pi halves of sine to the 2m theta d theta, instead of integrating from 0 to pi halves, what could I integrate from? What kind of symmetry does sine squared have? I could do negative pi halves to 0. It would be the same thing. So then that's the same as half the integral from minus pi halves to pi halves, which is the same as a quarter the integral from 0 to 2 pi. So this is just really the same as 1/4 the integral from 0 to 2 pi of sine 2m theta d theta. So if I can just do that integral, I divide by 4. And now when I start to replace sine with e to the I theta minus e to the minus I theta, it's going to be much easier. So this would then be 1/4 integral from 0 to 2 pi e to the I theta minus e to the minus I theta over 2I to the 2m d theta. And now when I expand it out, the only time I'm going to get a contribution is if the exponentials perfectly balance each other out. And so I'll just get, 1/4 the integral from 0 to 2 pi, 1 over 2I to the 2m, and it'll be 2m choose m d theta. So that allows us to be a little bit easier. And then one other thing that's just worth noting is the integral from 0 to 2 pi of sine squared theta d theta is the same as the integral from 0 to 2 pi of what function? Instead of integrating sine squared, what could I integrate? Cosine squared. So this is just 1/2 the integral from 0 to 2 pi of sine squared theta plus cosine squared theta d theta, which is just now going to be 2 pi over 2 or pi. So this is just a nice trick to integrate sine squared or to integrate cosine squared. But of course, you remember, it's probably bad that I'm now pausing when I say, of course, you remember, cosine x minus sine x is cosine 2x, which is the same as 2 cosine squared x minus 1. Therefore, cosine squared x is 1/2 cosine 2x plus 1/2. So if I want to integrate cosine squared x, I can now just integrate cosine 2x and integrate 1/2. So just a way to just remind you of some of the old calculus stuff you used to do, right? So if I get it down to just integrating cosine squared, I can be clever and I can notice the integral of cosine squared or the integral of sine squared is just 1/2 the integral of both of them. If I don't want to do that, I can then remember my angle addition formulas and replace my sines and my cosines. And now I'm reduced to just integrating a cosine and a sine. And of course, if I integrate from 0 to 2 pi, I know that that piece is going to contribute 0 because it's going to be an integral number of periods. So it's actually not going to be too bad to do. Okay, so anyways, I just thought it was worth revisiting the semicircle. Lots of ways to do this. The big idea is, depending on how you do the algebra, you can reduce the calculations you need to do. And if we are clever, and if we extend the integral from 0 to 2 pi, then we don't have to observe the fact that the imaginary part must be 0. It's still nice to do that, but we don't have to count on doing it. All right. How many of you have taken physics at a high level? All right. So if I give you 1-point mass under gravity, life is trivial. 2-point masses under gravity, life is trivial. Induction does not apply. 3-point masses under gravity, we cannot write down a closed form solution of where will things be at a given time. Imagine something like uranium with over 200 protons and neutrons. Much, much worse. The way subatomic particle physics works is you basically shoot things at things and see what happens. And the best explanation I ever heard is, imagine you want to understand how a grandfather clock works. So what you do is you take 2 grandfather clocks, you accelerate each one of them to 99.99% the speed of light, smash them together, look at what comes out, and use that to deduce the internal structure of the grandfather clock. That is what nuclear physicists do. I got to spend 2 summers working in a nuclear physics lab. Sadly, I never got to smash things like that. I was more on the theoretical side. So the question is, how do you deduce useful information from something like this? Well, it turns out in quantum mechanics, the fundamental equation is the following. And so when we look at the equation, H is the Hamiltonian, En are the energy eigenlevels, and Cn are the energy eigenfunctions. So this is a linear algebra problem. So those of you who've heard me give this lecture before, this part will be familiar. There are 2 things that prevent this from being a linear algebra Math 250 assignment. The first is H is infinite by infinite, and usually in linear algebra, in the first course, you don't deal with infinite by infinite matrices. The second is, I want you to diagonalize this matrix, but I'm not going to give you any of its entries. And normally in a first course in linear algebra, we at least tell you the entries of the matrix when we ask you to diagonalize it. So infinite by infinite, don't know any of the entries. Good luck. Right? Wigner, the same Wigner that we've been talking about, basically said, screw that. Let's use some insight from statistical mechanics. If I want to calculate the pressure on this wall, I need to know where each molecule is. I need to know where it's traveling, how fast it's traveling. And then I can calculate how many of them hit the wall in a small amount of time. Anybody know within 5 orders of magnitude how many EM molecules there are in this room? Within 5 orders of magnitude. Basic physics or chemistry. You should be able to give it to me within 5 orders of magnitude. Nobody knows enough basic physics or chemistry?
10 to 15.
10 to the 15. Yeah. Nope. You are not within 5 orders of magnitude. 10 to the 30. Oof. 10 to, I'm more comfortable with 10 to the 26. So this a mole is, I think, 6.02 times 10 to the 23rd.
Yeah, that's like 22 meters.
And so if I take 6.02 times 10 to the 28, 5 orders of magnitude gets me down to a mole and up to, 10 to the 10th moles.
Probably closer to like.
I don't think we have more than 10 to the 10 moles, and I think there's at least 1 mole of air in this room. Does this sound vaguely familiar to people from chemistry classes? So to be within 5 orders of magnitude, it's at least 10 to the 23, at most 10 to the 33. Good luck trying to write down the physics of 10 to the 20 plus particles. Wigner's great insight was, for each configuration, we can calculate the pressure, average over all configurations, and then most configurations will be close to the system average. And so if you can compute system averages, then most things will be close to that. So rather than calculating the matrix that corresponds to uranium, let's look at a random matrix, calculate its eigenvalues. Take another random matrix, calculate its eigenvalues, average over all these matrices, and then uranium should be close to that. So that was his great insight. And then depending on the physics, you might actually have some constraints on the matrix. Maybe the matrix is real symmetric, maybe it's complex emission. And so we will do a very simple case of, let's assume we have a matrix where the entries are independent, identically distributed random variables. We'll assume the matrix is real symmetric, so Aij is Aji. And so the probability we choose a matrix is just going to be the product of the probabilities of the independent entries. So has everybody seen enough probability that everything I'm doing here is fine? Probability densities are non-negative, they integrate to 1. Okay. If you want to expand this out, it means what's the probability I choose a matrix where the ijth entries in the interval alpha ij, beta ij? Well, I would just integrate my density from alpha ij to beta ij, and I would just multiply this by all of the pairs. And so that's why I'm doing it over all pairs, 1 less than equal to I, less than equal to j, less than equal to n. Because I don't choose 1, 2, and 2, 1. Once I've chosen 1, 2, 2, 1 is forced on me because the matrix is real symmetric. So I want to understand the eigenvalues of A. But it's not A is not screaming at me eigenvalues. It's screaming at me matrix elements. So I need a formula that allows me to go from matrix elements to eigenvalues. And this is one of the big themes in mathematical physics. Take what you can do and convert the problem you want to what you can do. This is the law of the hammer. Go to the land of the screwdriver and take the problem and convert it to something you can use your hammer with. So what we're going to do is, we talked a little bit about this last time. I'm going to attach a point mass at each eigenvalue. So here's my point mass delta. Here's my eigenvalue, lambda I of A. And I'm going to go over all the eigenvalues. Now you might notice that I'm not attaching the point mass at the eigenvalue. I'm dividing the eigenvalue by 2 square roots of n. That's just renormalizing things. Which do you think is more important, the factor of 2 or the factor of square root of n? Square root of n. The square root of n tells me how the eigenvalues change with the matrix size. As the matrix size grows, it turns out the eigenvalues get larger. The 2 is so I can say semicircle later in the day rather than semi-ellipse. The 2 is not that important. Why do I have a 1 over n? Well, I have n eigenvalues. So if I want to have a probability distribution, I have to somehow assign 1 I have n eigenvalues. The simplest thing to do is just each eigenvalue gets mass 1 over n. And we talked before that what is the delta point mass? If I integrate a nice function against it, it just returns the value at the point mass. If you want, you can think of f as a nice function, say it's differentiable, and think of the delta function as a limit of Gaussians of ever smaller standard deviation. And in the limit, as you do that, it's going to converge to a point mass. So the question is always, how do you make a subject like this rigorous? So I can approximate these point masses with a Gaussian with 1 over n. And as n goes to infinity, it's going to converge to all of my mass is just at that point. But at each finite moment, I'm going to have something that's nice and easy to work with. And you can quantify all the errors. And so this gives me my probability measure. And now what I can do is if I integrate this from a to b, that's going to calculate how many normalized eigenvalues do I have in the interval ab. And if I want to calculate the kth moment, I just integrate x to the k times the measure. And that will give me the kth moment. Well, if I look at this, I'm integrating this against 1 over n times the sum. So this plus 1 over here is coming from the 1 over n. The n to the k halves is coming from the 2, or the 2 n to the k halves is coming from the 2 square roots of n. I'm raising something to the kth power. I've got 2 root n. That's the 2 to the k to the halves. And then I've got the eigenvalues to the, and that's going to come over here. And now we use the eigenvalue trace lemma that the sum of the kth powers of the eigenvalues is the trace of a to the k. If you haven't seen that, if you just know that the sum of the eigenvalues is the trace of the matrix, calculate the eigenvalues of a to the k. The eigenvalues of a to the k are just the eigenvalues of a raised to the kth power. And that just gets you the formula. So is everybody comfortable at a high level of the kth moment is just going to be related to the trace of a to the k? And then this is where you take an advanced probability class between now and Tuesday. Okay. Homework. And in that advanced class, you will talk about when do the moments uniquely determine a probability distribution? And the answer is sadly not always. So it is possible that you could have a situation where the moments do not uniquely determine the probability distribution. There are nice distributions where that is the case. It's a generalization of the pain that the Taylor series does not uniquely determine the function. And I think we've looked at the function, g of x is e to the negative 1 over x squared if x is not 0, and 0 if x equals 0. The Taylor series of g is identically 0. Such functions should not, that's a value judgment. I'm not allowed to make value judgments. Life is interesting when such functions exist. This is like, you're not supposed to use the passive voice when you write, except if you're being extremely literary. You have a function which is 0 at 0. Its speed is 0. Its acceleration is 0. Its jerk is 0. Its snap, crackle, and pop, the next 3 derivatives are 0. That's the name. It's snap, crackle, and pop. That's the next ones. Every derivative is 0 at 0. And yet the function is not identically 0. So the fact that such functions exist is challenging. This is why real analysis is such a hard subject. Complex analysis is much easier. Complex analysis does not allow such functions in. This function is infinitely differentiable as a function of a real variable. If you try to look at it as a complex variable, e to the negative 1 over z squared, if z equals y goes to 0, the function goes to plus minus infinity. So if I approach 0 along the x-axis, the function goes to 0 very rapidly. If I approach along the y-axis, it explodes. This function, not only is it not differentiable, it's not even continuous. Complex analysis is very picky about what functions it allows to be differentiable. In real analysis, to be differentiable, oh good, left limit, right limit, they're the same. Not many options. Complex analysis, all those different paths you can take, they all have to give the same. It's far more restrictive to be complex differentiable. It's not surprising that you get a lot more out of that. All right. Oops. All right, so now that we have this success, the big result from Wigner, and this is not the most general statement you can have, there's a whole industry of what is the weakest condition you need to prove something like the semicircle law. This is being recorded, so I will just say I am happy to not state the most general version of the theorem. Yeah, I will assume that my entries are chosen from a probability distribution with mean 0, variance 1, and finite higher moments. You can do weaker than that. And then in that case, for almost all matrices A, as n gets very, very large, the normalized eigenvalues converge to a semicircle. And the key ingredient is the trace of A to the K is the sum of the eigenvalues to the K. This is the eigenvalue trace lemma. How many of you have seen this in a linear algebra class? The diagonal entry, sum of the diagonal entries is the sum of the eigenvalues. Did they ever tell you why you care about that? No, normally they don't mention at all why you care about this. This is just a fact. If I have a 2x2 matrix, I can use the trace and the determinant, figure out what the eigenvalues are without writing down the characteristic polynomial. Big deal. Once you get to 3x3, 4x4, why do I care about something like this? This is a general principle, and that's one of the things I really want to emphasize in this class. You want to study something, great. Hopefully other people care about what you're studying. You want to study something. You need to find a way to get your hands on it, to get information out of it. How can I get my information on the eigenvalues? I need to know what they are. If I have a 2x2, 3x3, 4x4 matrix, I've got explicit formulas for the eigenvalues. In fact, I was even doing that in probability today. I give you a 4x4 matrix, I can write down explicitly what the eigenvalues are. I can't do that for 5x5 and higher. What do? Well, we can approximate them. We need some way to get our hands on them. And it turns out that the eigenvalue trace lemma is the way to do it. And if you think about what's going on, if I multiply both sides by 1 over n, if you know probability, this is the expected value of the, well, all right. This becomes the kth moment. So really, it's not a big deal to just divide both sides by n. So if I can calculate the expected value of the trace of A to the K, that gives me the expected value of the kth moment. And then hopefully I'm in a situation where things are nice. And if I know the moments, I know the distribution. That's not always the case. But there's a whole slew of advanced theory that tells you when knowing the moments tells you what's going on. We're not going to cover that, but it can be done. It can be made rigorous. And so again, if I'm not providing enough detail, please let me know. There was a request to do random matrix theory in this class. We have the flexibility of doing things. There's a lot of great topics related to this. I want to do enough so that you can follow what's going on. If you want more detail, either speak up now or email me later. When I was a first-year teacher at Williams, I was teaching differential equations in the spring. Linear algebra was not a prereq. I see several of you rolling your eyes, and you are correct to do so. Linear algebra should be a prereq for differential equations. It makes it hard to do systems of differential equations if you don't know linear algebra. I needed to do 2x2 matrices, but that's not a prereq. So I asked the students, is everybody comfortable with 2x2 matrices, or do we need a review? Does anybody want a review? Nobody wanted a review. Nobody was willing to say they wanted a review. And I'm so old. I've been here for so many years. This was before cell phones were prevalent. We had clickers. Everybody had a clicker. And I said, if you want a review of 2x2 matrices, press 1. If you don't want a review, press 2. I won't share the response with the class? I'm just curious. It's not like 43 or 47%. I'm sorry. I never said I wouldn't share it with other people. I just said I wouldn't share it with the class. 43 or 47% wanted a review. 0% were willing to raise their hands and say they wanted a review. I'm sharing this so that if there's something that you want to see, please speak up. Almost surely you're not the only one. I'm trying to guess how much detail to go into. I could easily be making a mistake by doing too much detail or too little detail. Please speak up if it's not enough for you to get big picture what's going on. So the hope here is that by calculating the expected value of the trace of A to the K, we've got the expected value of the kth moment. If we know the moments, we should know the distribution. There's some advanced theory that would allow all that to happen. And the trace of A to the K, you expand that out, that's a polynomial in the matrix elements. I'm choosing the matrix elements independently from some probability distribution. I can now calculate stuff like this. All right. So before we do the calculation, we were dividing by 2 square roots of n. So I should justify where the 2 square roots of n comes from. So the trace of a squared is just the sum of the eigenvalues of a squared. Well, the trace of a squared is the sum of aij, aji. Well, that's just the sum of aij squared. But because I'm choosing my entries from a distribution with mean 0 and variance 1, this is just the variance of the ij entry as the mean is 0. If you want, you can do this as, aij minus 0 squared. And so if I calculate the expected value of that should be 1. I have n squared choices for I and j, so I expect this to be of size n squared. So the sum of the squares of the eigenvalues is of size n squared. There are n eigenvalues, so on average, each eigenvalue has to be of size square root of n. Does that make sense? Yes, no?
Just looking after about.
Well, just an order of magnitude, what I would expect is the average value is going to be of size square root of n. And if you're looking at the sums of the squares, each square is going to be of size n. There can't be any cancellation by sign because the eigenvalues are real. I have n objects. It's got to sum to n squared. So I expect each one of them to be roughly 1 over n times the total. So each one should be roughly of size n. So each one should be of size square root of n. So this gives you the correct scale. It's not going to detect a factor like square root of 2, but it is going to give you the n dependence. So I expect the eigenvalues of an n by n matrix to be growing like square root of n. It's really nice to be able to do a quick calculation like that. Okay, so now recall the kth moment is the trace of a to the k over powers of 2 powers of n. So the average kth moment, or the expected value, is I just take this quantity and then I multiply that quantity by the probability I chose that matrix. And then I integrate. Okay? So all we have to do is just do that calculation. So then we compute what that average is. Imagine I tell you I've got 2 million objects and the average is 1. 2 million objects, everything, if I average everything, I get 1. Do you think every object is close to the average? No, I could have half of the objects 0 and half the objects 2. Look, the average is 1. Nothing is close. So it's not enough to calculate the average. But if I can also calculate the variance and show that things get tight, then I can appeal to advanced results in analysis and probability. And so it's a 2-step process. You first calculate the average, and then you show that the variance is getting small, so things get tight about it. If you've heard of Chebyshev's theorem, that's often enough for something like that. Okay, so we just have to calculate these averages. So let's do a completely misleading calculation. Let's calculate the average of the second moment. I have no idea why I have AJI, not AIJ. Does it matter? No. So I want to calculate the trace of a squared, multiply by the probability that I chose the matrix, and then integrate over all possibilities, and then I divide by 1 over 2 squared n squared. This is from the 2 to the k n to the k halves plus 1 with k equals 2. Okay, well, if you look at the calculation, I can split it up into, for a given pair ij, I have the time aij hits paij, and then I have everything else. Oops. And then I have everything else. What does this integral, what does the blue integral equal? Oops. So I'll make the blue actually cover the integration sign. What does the blue integral equal? Y is 1 as the variance. What about the red integral? What does each red integral equal? 1 as, say, probability distribution. And so we see that the product is just 1, so I get just 1/4. And then we have the very misleading, the higher moments involve more advanced combinatorics. So sometimes when you look at a small case, it can be very misleading as to what goes on. Because I'm just looking at the second moment, there's not that many things that can happen. My polynomial is just aij aji, which becomes aij squared. As we get higher and higher, we have more and more terms. So now I have to look at something like this. And so I now need to look at, this is now my polynomial. And I multiply that by the probability I chose the matrix, and then I do these integrals. And that's what we're going to look at today now, is how to compute these. So have we done enough motivation to explain why this is what we're looking at? People are fine with this. This was enough detail. And now we just have to calculate this. So the difficulty is going to be figuring out what terms contribute. So again, we have I1, I2, I3, I4, all the way up to IK, I1. And so the first thing is we're going to show the odd moments vanish in pairs. So we have A, I1, I2, A, I2, I3, A, I3, I4, dot, 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 A, IK, I1. We wrap around. And we have some nightmarish expression. Oh, I don't think I can copy this because that's text, because that's an image. And so I don't think it does not do that. All right. So we have to calculate the expected value of A, I1, I2, A, I2, I3, A, I3, I4, dot, 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 A, IK, I1. Right? That's what we're getting from the trace. We have to calculate this expected value. And each A, IL plus 1 is drawn from a mean 0, variance 1 distribution. Okay? So for example, maybe one of the terms is we have the expected value of A14, A47, A72, A27, A74, A48, A81. A74 is the same as A47. A72 and A27 are the same. And nothing else is the same. So this would be the same as the expected value of A14, A47 squared, A27 squared, A48, A81. So how many of you have taken a class in probability? Yes or no? All right, do you know that the expected value of a product is the product of the expected values if they're independent? Okay, so if they're independent, then the expected value of a product is the product of the expected values. This would be the expected value of A14, the expected value of A47 squared, expected value of A27 squared, dot, 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 dot. What's that expected value going to be? 0. This is 0, this is 1, this is, it doesn't matter what the other ones are. Because I'm drawing the A's from a mean 0, variance 1. If I have something that's not matched, it contributes 0. So when I look at my trace, everything has to be matched with at least something else, or it's going to contribute 0. It's possible everything is matched with everything. I could have A12, A21, A12, A21, A12, A21. I could have A11, 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 A11. Okay, but I can't have anything unmatched. If anything is unmatched, it contributes 0. So everything is matched in at least pairs. So matched in at least pairs. Okay. So the next thing is to show that if you ever have a triple matching, it's insignificant. And what do I mean by insignificant? I mean that in the limit, it doesn't contribute. So remember, we divide by 2 to the k n to the k halves plus 1. So what we can do is the following. Look at a term. See how many terms we could have like that. See what the maximum contribution they could give is. And if that is going at a slower rate than n to the k halves plus 1, it's not going to contribute in the limit. At a high level, that's what we're trying to do. So as soon as we have a triple matching, we're going to be in trouble. Okay, so assume matched in pairs or more. Okay, if I have an odd moment, is it possible that everything is matched just in pairs? So is it possible that everybody is paired off with exactly one other object if I have an odd number of things? There has to be at least a triple matching, right? So if odd, k equals say 2m plus 1, at least one triple matching. So if you think about what's going on, we have I1, I2, I2, I3, I3, I4, dot, 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 I2m plus 1, I1. And maybe, here is maybe I8, I9, I don't know. Maybe I have matchings like this. What would it mean for them to be matched? And actually, let's use different colors. And maybe this is my triple matching. Maybe it's not good to actually have that as the triple matching. I just want to have something like somewhat generic. I6, I7. So I'm not doing anything that's neighbor. You can handle those cases later, but let's say we have matchings like this. What does it mean for things to be matched? Well, so I need AI2, I3 to equal AI8, I9. So what's the only way these can be the same? How could these be the same variable in my real symmetric matrix? So what does that tell me? So either I2, I3 equals what? Or I2, I3 equals I9, I8. Okay, well, worst case, I have two possibilities. 2 is a finite number. As long as the number of possibilities does not grow with capital N, with the number of indices, with the size of the matrix, as long as it's independent of the size of the matrix, I don't care what power of 2 I get. If I have 2 to the k 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 to the k, I don't. But if I had something like that, that's independent of n. It's just some number. So here I have two possibilities. If I want them to be the same, how many free parameters do I have of the I2, I3, I8, I9? So let's think about it. I can choose I2 and I3. I can choose, but choosing which one they match to, that's a factor of 2. I don't care about that. So I have two free parameters, I2, I3. But then I have I8, I9. I can choose one of I8, I9. No, they're both forced now. So of these 4 indices, I have 2 that are free. What if I have a triple? So for the triple, I should have done this in red. If I now have A, I, 2m plus 1, I1 equals A, I3, I4 equals A, I6, I7.
Oh, yeah.
So, here I have 4 variables or parameters. I2, I3, I8, I9. Choose I2, I3, then I8, I9 are forced up to a factor of 2. Right. If I now give you something like this, I have 6 parameters. I1, I2m plus 1, I3, I4, I6, I7. Choose I1, I2m plus 1, other 4 forced up to a factor of, I think now it's 4. So when you think about it, for every pair that I have, if something is paired with exactly one other, of my 4 indices, I really only have 2 things that are free. If I have a triple of my 6 indices, I only have 2 that are free. One of the things you have to be a little bit careful about is, well, I'm doing things with I2 and I3, but I1, I2 is matched with something. And these both share an I2. So if you think about it, the pair I1, I2, it has 2 things that are free. And then once you specify which pair you have, whatever it's paired with is now stuck. For the next element as I go along, I could potentially have 2 more things that are free. Maybe one of them is not because I've got I2. Unfortunately, what if I2 happen to be matched, it can't be in this case, but what if it was matched with I2, I3? If it's matched with I2, I3, then that means I3 is just the same as I1. It's almost as if I could just lift that up. And that's where we're going to see the difference between crossing and non-crossing. If you're matched with, there you go. If you're matched with the thing right next to you, then the two I2s are the same. So I3 is the same as I1. Just remove it and you reduce to a lowercase. So when we think about what's going on, one of my advisors was phenomenal, Professor Vanyas, at counting with fingers. So we have K indices. How many tuples? So for each index, how many choices do we have for it? I1 takes on how many values? N. So we have K indices, so how many tuples do we have? N to the K. But we just showed that whenever things are matched in pairs, for those 4 tuples, we lose at least 2 of them. And when you have something matched in a triple, you lose at least 4. So matched in at least pairs with a triple, how many tuples? Some function of K, I don't care what it is. Some function of K, right? Everybody agree it's some function of K? This is high-level mathematics. We don't need to worry about what it is. If we cared about the rate of convergence, absolutely. I don't care about the rate of convergence. How many tuples do we have? Well, each pair, what's the best case for how many, if everything was matched in pairs, how many pairs do we have? I'm sorry?
Number of tuples of it.
And so, what would that be? So if everything was perfect, this is what we would have. Right? So we have to be a little bit careful because the very first tuple, we have 1 extra degree of freedom because we have what we start with. And then remember, for all the other tuples, information is being, this is where things get a little bit annoying, information is being pushed onward. And so, if I have a pairing with 4 indices, at most 2 of them are free. So if I split everything like that, the way to look at it is every pairing is going to give me 2 out of the 4 indices. But remember, these indices are occurring in other places as well. And so you got to be really careful about overcounting. And so as we're coming in, think about it as we're coming in over here. Once I've done what I1, I2 is matched with, I2 is now forced on me. So I don't have 2 new free things. Each new matching is only contributing 1 new thing. The very first one starts off with 2 free indices, I1 and I2. Every subsequent one gives me 1 new thing. And so if I really think about what's going on, I start off with 1 from, I1 is free, and then that pairing, I can choose I2, and then the other 2 indices are forced in that pairing. And then each new pair gives me 1 new free variable because I propagate over. And again, if I'm matched with my neighbor, then I2 is the same as I2, I3 is the same as I1. So now I3 is the same as I1, I4 becomes my free thing. So it just pushes it down. So now all the remaining pairs give me one more freedom. How many pairs do I have? I'm sorry? Not k over 2. Because remember, we're assuming k is odd. We have m pairs. Or is it m minus 1?
Yeah, so that's k minus 1.
So your best case, I think it's your m minus 1 pairs, and then we have the triple where we lose even more. And so if I'm thinking about what's going on, n to the k halves plus 1 would be n, if k is 2m plus 1, it'd be to the m plus 3 halves, I think. And so I have the plus 1 from the beginning, and then how many pairs can I have? So, in something like this, it's always good to just, let's write something down. Let's k equal 11, something big. 1, 2, 3, 4, 5, 6. Well, 11 is too big. Let's do 9. 6, 7, 8, 9. So we have one triple. Let's say 5, 7, 9. We have a double here. And let's say we have so let's think about what's going on. From the gold, we start off with 2 parameters, right? That passes a value onto the second pair. And this now gives me a plus 1 more parameter. Now, when I look at that, that passes knowledge onto here, which we already had, and that passes knowledge onto the first element here. We now get plus 1 more parameter for all of that stuff over there. And now that's going to pass some knowledge into here, and that's going to give me plus 1 parameter. So we should get, when the dust settles, I think we get 5 free parameters. Or there's going to be some constant times n to the 5th. N to the k halves plus 1 is n to the 9 halves plus 1 is n to the 5 and 1/2. And so if I look at the contribution is going to be something of order n to the 5th, divided by something of n to the 5.5. In the limit, it's going to be 0. And so the question is, what is this contribution going to be? The contribution here is going to be the second moment 3 times, times the third moment 1 time. So this is going to be less than or equal to the largest moment of the first k moments to the 4th power. Because what I can do is I can say, look, I'm going to have things matched in at least pairs. I might have a triple. I might have a quadruple. I can't have more than everything matched together. So if I look at one of the configurations, it's going to be at most the kth moment. Or it could be products of maybe the second moment a couple of times and the third moment, or maybe a couple of 4th moments and a 5th moment. Screw that. Look at the first k moments and look at which moment is the largest and replace every contribution with that. You're only going to make things larger, and you're not going to make things larger in a way that grows with n. You can see now why nobody wants to write this down. This is ideal for writing on the screen and just talking informally. It's painful to write this up. But the idea is, look, whatever the contribution is, I can bound the contribution of a given matching independent of n. And the number of matchings I can bound as a power of n to a smaller degree than n to the k halves plus 1. Therefore, in the limit, this doesn't contribute. So is this enough detail that people are happy that the odd moments don't contribute? A faster proof is to just assume you have a distribution that's symmetric about 0, so all the odd moments vanish. But not every distribution is symmetric about 0. But if you were to choose such a distribution, much easier calculation. Why am I not doing that? No, we actually have a bunch of lectures to get through to fill up the semester. No, I'm not doing this just because we need to fill up the semester. I'm doing this because when we look at the even, I mean, it's not a bad thought. No, the reason I'm doing this is because when we get back to the evens, I want to show that the only even case that matters is when the evens are all matched in pairs. And by doing this argument here, you can now say, if there was a triple among the evens, there's either a quadruple among the evens, or there's 2 triples, or something like that. And again, this degree of freedom argument. And the question is, what is the cleanest way to write up that we have a lower thing? When I was trying to write it up like this, is this getting confusing in terms of, what's the power over here, and just, what's going on here with the exponent? I thought it was easier than just backtrack and just go like this, march down, and see, look, indices are propping over here. I've got over here I1, I2. Here is I2, I3. I2 is new. I3 becomes the new one. And just marching down like that. And you can see that it's not going to contribute. So we know we don't have to worry about the odd moments. And we don't have to worry about the even moments except when things are matched in pairs. That's not bad. So now we have, let's say, 2 M objects. We want to match in pairs. The number of ways is, and if you're grading for me in probability, you're not allowed to say anything. Because I think we might be doing this in probability. Does anybody know the number of ways to match 2 M objects in pairs?
Oh, we could do that yesterday.
Or did we do this yesterday? Okay, I wasn't sure if we had done this in here as well. Okay, we did do this. Is 2M minus 1 double factorial. So if each pairing contributes fully, it's bounded by Gaussian. So if each, let's say, matching in exactly pairs contributes fully, you get the Gaussian. So in some sense, we have an upper bound for the moments. It may not be the case that every matching contributes fully. And it could be the case that, when I'm matching things, let's say I have AI1, I2, AI2, I3, AI3, I4, AI4, I1. And I could match like this. But maybe all are equal. That would be a 4th moment. But if you think about it, how many ways could they all be equal? So I1 is free, I2 is free, and then rest are mostly fixed up to factors of 2. Because if once I1 and I2 are forced on me, if I want that to also equal AI2, I3, then I3 is forced on me now, up to the order in which I. And so now I would only have 2 degrees of freedom, and I'm dividing by here, it's 1 over 2 to the k n to the k halves plus 1. Since k equals 4, this would be 1 over 2 to the 4th n cubed. If I only have n squared, objects, if I have a quadruple matching, it's not going to contribute. So when I'm matching things in pairs, okay, well, the probability that they're all the same is negligible as n gets really, really large for any fixed k. Yes, once I tell you, I1, I2 is matched with I3, I4, I can't use that same value for the other one. But the probability that they align is so insignificant, don't worry about it. Just keep it free. It's going to be a lower order term. And that's one of the great themes in mathematics. If something is low order, as long as you can keep track of them and you don't do it too many times, they're not going to be important. Okay, so now we want to count the number of non-crossing matchings. I've said it's the Catalan numbers, so we have to somehow convert this to Catalan. Catalan is walking so that we don't cross the main diagonal. How is that related to the crossings here? And so I'll just draw a bunch of things like this, okay? We want to look at how many ways can we match them in pairs so that we don't cross. Okay, so let's call this the first index I1. Does everyone agree that I1 has to be matched with something? So let's say I1 is matched down here. What must be true about this?
Equivalent to be under the diagonal. So that we cannot go to the other side.
So they all have to be matched amongst themselves without crossing, right? And what must be true over here? Right? So this is matching 6 objects, no crossing. This is matching 8 objects, no crossing. Doesn't that seem a lot like what we did before with the Catalan numbers, where if I want to stand at the diagonal, I look at where's the first time I hit? And what we did before was when we wanted to stay below the line, we looked for the first hit. And if that's the first hit, we had to basically have some path that stayed. And I could allow myself to hit that multiple times if I wanted to, but I can't hit the diagonal until that point. It's the same thing here. So if we let Cn equal the number of ways to match, and this is where things get annoying. Do we want to have an even number? Do you want to have n, the indices be forced to be even, or just say Cn is the number of ways to match 2n objects in pairs on a circle without crossing? So if you look at it, how many where could 1 go? I could match one can be matched with what? I could match it with 2. Could I match it with 3? No. Could I match it with 4? Could I match it with 6? So I can match 1 with any even number. And so what we would get is Cn would be a sum. K goes from 1 to n because I have n possibilities. If I match it with 2, that's basically going to be C0. I have no ways of matching. Yeah, let's do it without a sum. So I could match 1 with 2, and then it would be C n minus 1. Or I could match it with 4. And if I match it with 4, then I have 2 objects that I have to match. That's going to be C1.
Is the reason why we cannot do 3 because there will be 1 left?
Yeah.
Yes.
Yeah. And everything has to be matched in pairs without crossing. So if I match it with any odd number, there's an odd number of things, and at least one of them would have to cross the line. So then that would be C1, C n minus 2 plus dot dot dot. So it should be something like, the sum, CK, C n minus maybe I think n minus 1 minus k, something like that. K goes from 0 to I think n minus 1, something like that. Again, up to small errors, this is what you get. That's the Catalan recurrence. So what we've just shown is that the number of ways to match 2 n objects on the circle such that you don't cross any lines when you match is just the Catalan numbers. And now the question is, can we show what the contribution is from these matchings? And what are the contributions from the matchings where you have a crossing? Well, we still have like 2 minutes left, so it's plenty of time to do something. So AI1, I2, AI2, I3, AI3, I4, AI4, I5, AI5. How much time do I have? AI6, I7. So if I just keep writing this for enough time, I'll be fine. So let's say I have your matching like this. Okay. And then I'll worry about the rest later. So boom, 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 it's going like this, and then boom, 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 going like that. Well, if these are matched, what can you, whoops. Come on. All right, well, we'll do it like that. What can you tell me about, because these are matched, what can you tell me?
Yeah, 3 equals, or I3 equals I5.
Good, I3 equals I5, because they're matched. Now that I know that I3 equals I5, this over here is really, I guess I'll write this in green. This is really AI3, I6, and this is AI2, I3. What do we know about these? I2 equals I6. And so this over here is really AI2, I7. So what can we deduce? I1 equals I7. So if we do have, there we go. So if we do have everything matched in pairs, what I hope you're seeing is, I can just keep lifting, 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 lifting. Everything is going to be really nice. And the contribution is not going to be hard to figure out. Do you have to have something matched with something that's adjacent to it if everything is matched in pairs?
If you don't cross.
Yeah, if you don't have crossings, if we don't have things matched with its neighbor, then this has to go down there somewhere. This could go down there somewhere as well. Right? So is everything going to go down there? Can everything be matched down there? So you need to somehow make that rigorous. That there's got to be, that when you're doing it like this, this should be something you should be able to do by induction. That if I don't have myself matched with a neighbor, there's going to be no way to do it. Eventually, something's going to be pushing to the same place.
Yeah.
So I'll let you think about that for Tuesday, because I think today is Thursday. So this is a good place to stop. to the right.